morning. I hope you're all having a good day so far. Today you're going to teach yourself the first part of 2.13. And what this is going to cover over the next couple of lessons is how to solve exponential and logarithmic equations and inequalities. And today we're really just going to focus on the equations part. We're going to use some log properties that we've covered in the last couple of lessons to help us solve these equations. We've learned how to use those log properties to simplify expressions and to kind of find equivalent representations. But now we're going to use those same log properties to help solve equations today, and the next time we'll talk about inequalities. So here are just kind of a recap there of the log properties and how to, in our most recent lesson, how to expand or condense logarithms. So all of that's going to come together today, and then again, how to kind of switch from exponential form to logarithmic form, forwards and backwards there, okay? So first thing we're going to do is we're going to look at equations with only one logarithm or exponential in them. And if an equation or inequality involves only a single logarithm or only a single exponential, we can solve by converting between the forms. So convert between forms. That's why you have to know this rule really, really well. The base of the log is the base of the exponent. Just remember that the whole entire point of logarithms is to get the exponent alone or isolated. That's why the exponent over here in exponential form C is all by itself in logarithmic form. And then again, I'm going to be using this word a lot today. In a logarithm, whatever is sitting right here is called the argument. And that just kind of helps me teach you, because there's something specific you have to know about the argument in the lesson today. Okay? We've got the base, the exponent, and the argument. So here are the steps to solve exponential and log equations that only have one log or exponential in them. The first thing you're going to do is isolate get the logarithm alone, essentially. Get the log or exponential alone on one side. So that might involve adding or subtracting a constant or dividing by something, because we want to get the log alone or we want to get the exponential base alone. Part 2 there is just write the equation in the alternate form. So if it's in logarithmic form, switch it to exponential, and vice versa. 3, solve for the variable, and then 4, simplify or round answer as directed. So if you'll notice right there in example 1, it does say leave your answers in exact form. That just means we're not going to grab a calculator and come up with a decimal answer. We're just going to leave it in the exact form, which you'll see here on example 1, part A. Well, this is clearly an exponential equation. We don't see the word log, or we don't see ln for natural log anywhere, so I need to solve for this exponent x. The very first thing I'm going to do is to isolate this 4 to the x power. I need to get that alone. So what I'm going to need to do to make that happen is add 2 to each side. And I'm not going to show that work. 7 plus 2 is 9. Okay? Now what this says is 4 to some power is 9. I don't know what that power is. It's some decimal value. What we need to do next then is we need to write this exponential equation in its alternate form. That's going to be log base 4 of 9 equals x. Well, how did that help us? Well, now technically I could pick up a calculator and have it calculate for us log base 4 of 9. That is the decimal value. That 4 could be raised to that power to equal 9. But because the directions said to leave it in exact form, this is it. We've solved for x. Log base 4 of 9 is what x is. So we're just going to leave it alone right there. Okay? B. Clearly, again, this is an exponential equation that we're needing to solve because we don't see log. I do need to get 2 raised to the power. I need to get that alone. So to do that, I'm going to subtract 5 from each side. That's going to leave me with 2 to the x plus 3 power. I'm not really sure why there are parentheses around this 2. It's not really necessary. Then I'm going to subtract 5 from each side. 26 take away 5 is 21. Now that the exponent is alone, I can switch to logarithmic form, which is going to be log. The base up here is 2, so that's the base of the logarithm. The exponent this time is not just x, it's x plus 3 That's going to go over here, and the argument is 21. Well, just like I told you on part A, this is some decimal value here, but we're not going to crunch that number. We're going to leave that alone. But what I do need to do to solve for x is I need to subtract 3 from each side. That's going to look like this. Log base 2 of 21 minus 3. Now, parentheses become really important here because I'm not really needing to take the log of 21 take away 3. It's log of 21. I'm going to throw some parentheses around that to indicate that's the argument of the logarithm. And then from there, I would subtract 3. But again, we're not going to pick up our calculator and do that. This is its exact form. Kind of like your teachers tell you to leave a fraction as 1/3 because that's more accurate than 0.3 repeating. C. We have an exponential equation here. We need to get this e to the x power alone. That's what we need to isolate. The base of the exponent needs to be alone. So what I'm going to have to do first is, using some algebra skills, I'm going to subtract 3 from both sides. So -7 take away 3 is -10, and I have to do that first before I can get rid of the coefficient -4. So we're subtracting 3 from both sides. And in this problem now, I need to get rid of the -4 that's being multiplied by the base. So I'm going to divide both sides by -4. I'm not going to show that work. -10 divided by -4 simplifies to be 5 halves. Positive 5 halves. Okay? Now that the exponential expression is isolated, now I'm allowed to switch to logarithmic form. And because I have base e, instead of writing log base e, I'm going to write ln for natural log. So natural log of the argument equals the exponent, and the argument is the 5 halves, and it is important to put parentheses around that fraction when you're taking the natural log of the entire fraction. I could grab a calculator and see what decimal value I get, but I'm leaving it in exact form. So just to recap here, I did not show the steps. We subtracted 3 from -7. We divided -10 by -4, and then we switched to logarithmic form. How did I know to use ln instead of log? Well, instead of writing log base e, I just kind of thought ahead and thought, well, log base e is natural logarithm by definition. So those are pretty straightforward. Let's go to the back. Okay, we're going to do the same thing here, but these are logarithmic equations. You see the word log, log, you see natural log. So it's going to work the same way. I need to get the logarithm alone. And in this case, what that means is I need to get the log of the argument. That's what I need to isolate. That's what I need to get alone. I've got 2 steps that I need to do before that happens. The first thing I'm going to do is get rid of whatever's being added or subtracted, and then I'll divide by anything that's being multiplied. So I'm going to subtract 4 from each side. That's going to leave me with 2 log base 3 of x plus 3 equals 10 minus 4 is 6. Now I need to get rid of the 2 that's in front of the logarithm, so to do that I'm going to divide both sides by 2. 6 divided by 2 is 3. 6 divided by 2. Now the logarithm is alone. It's isolated on one side of the equation. Now is the point where I can switch it to exponential form. And that's going to be 3 to the 3rd power equals x plus 3. And if you'll notice, I kind of skipped over the directions here. We're going to leave these in exact form as well. That's going to switch over to 3 to the 3rd power equals x plus 3. Now, 3 times 3 times 3 is 27. And then we're going to subtract 3 from both sides to solve for x, and we'll be finished with this problem. So subtract 3 from each side. 27 take away 3 is 24. And that is exact form. We're going to do the same thing on B. If you want to kind of challenge yourself and press pause, work the problem and then skip forward, see if you've got it, that would be great. We're going to isolate the logarithm, so I'm going to subtract 2 from each side. The logarithm is alone, so now I'm going to switch to exponential form. It's going to read 5 to the second power equals 2x minus 1. 5 squared is 25. I'm going to add 1 to each side. And then I'm going to divide by 2. That one worked out nice and neat as well. We didn't end up with a fractions or anything. In part C, we've got a logarithm up here in the numerator, and that's what I need to get isolated by itself. In other words, the only thing I need to get rid of here is the divide by 5. So to do that, I'm going to multiply both sides by 5. That's going to read natural log of 2 minus x equals, 5 times 1, and multiply both sides by 5, is 5. Now, the log is isolated. That's technically log base e. So when I'm switching to exponential form, the base is going to be e. I'm going to raise it to the 5th power, and that's going to give me 2 minus x. Remember that e is just a constant, 2.718, so forth. So I'm just going to leave it like this instead of grabbing a calculator and raising e to the 5th power, because I'm just leaving it in exact form. What I am going to do next is I'm going to subtract 2 from each side. But that leaves me with negative x. Essentially, the next step is, in an Algebra 1 setting, we would show, oh, we're dividing everything by negative 1. But you're in an advanced math, so if you don't know this trick already, if you have solved for negative x, you can just switch the sign of everything, and that's going to give you positive x. So that would be negative e to the 5th power plus 2 equals x. Or you may see it swapped around where the 2 is in front, minus e to the 5th equals x. But either way, that's going to be the exact form. An exact form to me just kind of means, hey, you're not allowed to have a calculator in this part. Okay, let's talk about a different type of logarithmic equation, because those are pretty easy. If you have log on one side, these are the kind that we just worked, log on one side only. Then you just switch to the equivalent form. Take a second to write that down. If you have a logarithm on one side in the equation setting, you're just going to switch to the equivalent exponential form. That's how we solved right up there, example 2, a, b, and c. But we need to talk about how to solve equations that have logs on both sides. Like here, we've got log base a of x equals log base a of y. I think these will end up probably being your favorite, because there's a really cool rule here that just says, if you can isolate where there's just a single logarithm of an argument on each side, as long as the bases of the log match, then you get to just drop the logarithm, set x equals to y, and solve. So those become really easy. Here's the catch. Look at that important note 1. In either case, and we didn't do this before because I'm kind of baby stepping you into it, no matter what kind of logarithmic equation you're solving, you need to check for extraneous solutions. That's the number one thing people forget. It is kind of a pain, but I'm going to show you a little bit of a shortcut that makes it fast. Using log properties can sometimes lead to solutions that are not in the domain. So the first thing that we'll learn to do is see what the domain is supposed to be, and that will help you check for extraneous solutions in a quick manner. This is just here to say that don't be misled here. Like, if you have a log plus a log equals a log, you can't just drop all of those and say x plus y equals c. That's not how that works. Canceling out the logarithms only works when you have isolated logarithms on each side, okay? I'm not sure that that note needs to be there. It could further confuse things, but let's just move on and kind of look at what we've got here. Example 3, solve the following equations, and then it's really important that you don't just stop there, because in a multiple choice setting, I guarantee they're going to have some misleading answer choices. Check for extraneous solutions when necessary. Okay, let's start with that. Here's what that means. At the beginning of the lesson, I told you I'm going to be using the word argument a lot today. The argument must always be positive. So if I solve for x in the end and I get an answer like -8, okay? -8 is not going to work when I plug it back in right here, because -8 plus 4 would give me a negative argument. So right off the bat, we can set some rules and we can kind of see what our domain is supposed to be. And domain is just a fancy way of saying, what is x allowed to be? Well, here, I don't ever have to worry about this argument being negative because it's set. It will always be 3. But here we have a variable, so we need to see what are the boundaries of x that will always create a positive argument. You can just set this equal to 0 and solve. We know that x needs to be greater than -4. So I'm going to make a little note out to the side. X has to be greater than -4 when I solve. I'm going to do that for all arguments, including this one over here. If you set this one equal to 0 and solve, you're going to get +2/5. X has to be greater than +2/5. Now stare at these for a second. X has to be greater than -4 will be satisfied as long as this one is satisfied. So in other words, once you set all of your arguments equal to 0 and you solve, you're going to always choose the largest one. This is the domain for this equation. What that means is I've just figured out I'm going to go on my merry little way, I'm going to solve this, and no matter what answer I get, it's only going to be a solution if it's greater than 2/5. Anything smaller than 2/5 is not going to work. Okay? So here we go. We are going to use log properties from a couple of lessons ago to take this side and shrink it down. Again, you can't say 3 plus x plus 4 equals 5x minus 2. You're not ready to drop those logarithms yet. You have to condense this left-hand side into a single logarithm. We have log properties that say 2 logs being added together with the same base can shrink down into a product. So this is going to be log of 3 times x plus 4. I'm not going to do anything over here yet. Now I have a single log isolated on each side. So I get to do this really cool thing where those just cancel out and I'm just solving this linear equation. I'm going to distribute the 3x plus 12 equals 5x minus 2, and we're going to solve for x. So I'm going to, you should be able to handle this, but I'm going to subtract 3 from each side. I always like to keep my x values positive. I'm going to subtract 3x from each side. I'm going to add 2 to bring it over here to the left, and I'm going to divide by 2. Before I put a box around that or circle that, I need to make sure that it's in the domain. As long as the x values are greater than 2/5, then they work. It's okay to go back up here and plug in a 7 anywhere I see an x, because it won't cause an argument to be negative. So that is a valid solution. Let's go to B. These are logarithms. They work the same way as when you see log. Natural log just indicates that the base of the logarithm is e. If I look at these arguments and kind of figure out my domain, here I know that x has to be greater than -1. And here I know that x has to be greater than, that would be positive 5/3. And then the little shortcut is just go with the bigger one, because if x is greater than 5/3, then it'll automatically satisfy this part. So I'm going to solve for x, and I'm just going to make sure that my values are greater than 5/3. So here we go. We're going to work this one the same way. We've got a log minus a log, and I can condense that by using the property, the quotient property, that says that's going to be the log of this argument, that's the numerator, divided by this argument is the denominator. Because I condensed this down into a single logarithm, now I can use the property that allows me to cancel out those logs and just solve for x using some algebra. The problem here is I've got x in the denominator, so I am going to show a little bit of work here to make sure you're comfortable with this. I'm going to multiply both sides by this denominator, 3x minus 5. Or, yeah, I guess that would be the best way to tackle it. It's going to give us another option, but it wouldn't have really helped anything. That way, that that denominator cancels out on the left. And then in the next step, I'm going to go ahead and distribute this out. So I'm going to have x plus 1 equals 21x minus 35. I'm going to go ahead and bring my x's over here to the right by subtracting an x. And I will add 35 to bring it over here. That's going to be 36. And in the end, we're going to divide by 20. And 36 divided by 20 simplifies to 9/5. But before I circle that, I need to make sure that that satisfies the domain, the restrictions on the domain that say x has to be greater than 5/3. So if you're not really too keen on fractions, you might want to find a common denominator, okay, which will be 15, and just check that this is larger than 5/3, and it is, so that is a valid solution. Now part C, this is the first time we're going to get a couple of answers and only one of them is going to work. And you might be thinking, how are you going to get 2 answers to this problem? Well, we're going to end up with a quadratic situation here. But let's go ahead and just pause and make sure all of these arguments have to be positive. So here, x has to be greater than -2. Here, x has to be greater than +3. And this is the larger one. So that's the restriction on the domain. Here we go. We're going to shrink this down into a single logarithm. Log base 3 of x plus 2, I'm using the product property, times x minus 3 equals log base 3 of 14. Now I can drop the log base 3 on each side, and here's where you can start to see, oh, this is going to be a quadratic situation. I'm going to FOIL that out or distribute that out, and I'm going to end up with x squared minus 3x plus 2x, that'd be minus x, and then 2 times -3 is -6, equals 14. I'm going to bring the 14 over here to the left by subtraction, and that's going to give us x squared minus x minus 20. And because this is a simple trinomial, we can factor it really quickly into x minus 5 and x plus 4. -5 times 4 is -20. -5 plus 4 is -1. Set those equal to 0 and solve, and I would get these 2 answers. I'm going to end up with x equals +5 and x equals -4. But both of those are not viable because I just found in my domain all of my x values, anything I plug in up here, must be greater than 3. Otherwise, we might end up with a negative argument right here. So this is the only one that satisfies that. -4 is not a viable solution. You don't have to cross through it, but just indicate, if this was like a free response setting, indicate that that's your only answer because your domain is restricted here. This next one is pretty straightforward. Basically, this argument has to be, well, any number can go there as long as it's positive. So the restriction on this domain is just x has to be positive. X has to be greater than 0. Why am I not worried about this one? Again, that's permanently going to be 3. It's a constant. There's no variable in there, so don't worry about it. That's never going to end up a negative argument. So here we go. We're going to shrink this down into a single logarithm. So that's going to be natural log of, we're going to use the quotient property, x over 3. equals 2. Now, I want you to notice we don't have a log on each side, so we're going to solve this like we did those right up there at the top of the page. Once you have your logarithm isolated, switch it to its equivalent form and solve. So here, that's going to be log base e, so e squared equals x over 3. We're going to multiply each side by 3. 3e squared equals x. E is positive, so if I square it, I get something positive, but if I multiply it by 3, I get something positive. So without knowing this exact value, I know that it satisfies this restriction on the domain, so that is a viable solution. All right, let's go to the next page. And I'm actually going to stop this video here, and then the next video will walk you through the last, really, basically just one page of notes left. So that kind of helps to break it up.